Having dealt with refraction of light at the plane surface, we shall now examine the refraction of light at a spherical surface. It is the diagrammatic illustration of refraction of light at a spherical surface. That is what the diagram we have drawn. The spherical surface is either convex or concave, the curved surface. Here it is convex surface we have used, and this boundary, the spherical boundary, is separating the two media, that is media 1, media 2. These have differences in the refractive indices, here N2 and N1, and let us call this as N2 the higher value, and N1 is the lower value. And this will explain how the light bends when traveling between two media through a spherical surface. Now let us consider the light is passing from rarer medium to the denser medium. Rarer medium to the denser medium. So, we have to place the object on the rarer side on this line. It is called as principal axis. What is principal axis? The straight line, it is a straight line passing through the point C and point P. The point P is called as pole of the spherical surface, center point of the spherical surface. C is the center of curvature of the spherical surface. A line passing through is called as principal axis. It is also called as optical axis. The object O, the point object O, is placed on this line, this side like this. Well, let us consider a ray of light from the object in the direction as shown. This explains how the light bends when it is moving from one medium into the other medium. So at this point, the boundary surface, it undergoes refraction. Refraction because of differences in refractive indices. Because of higher value of N2, the light after refraction bends towards the normal. The light ray is supposed to pass like this, but not like that. It is bending towards the normal. What is the normal at this point to this surface? The normal to the spherical surface is always a straight line drawn between C and the point of refraction. This is the point of refraction for this ray. So this straight line is called as normal to the surface at this point. It is a point of refraction. Then the angle between this line and this line is called as angle of incidence, I. This is the normal, this is a ray incident ray. After the refraction, the ray is bending towards, that is from here to bending towards, angle of deviation here, bending towards the normal. this bending results in converging of ray to a point on the principal axis. This point is called as point of image formation. After convergence, this is the point of convergence. It is called as point object, point image formation. And this is the position of the image on the principal axis. The position of the image on the principal axis depends on the refractive index N2. If it is higher, more bending, and if it is lower, less bending. It will decide the position of the image on the principal axis. So in this diagram, we have some parameters. This is one parameter, refractive index of the rarer medium. This is another, refractive index of the denser medium. And along the principal axis, we have these points are there. This is a point of object, and this distance from P, that is between P and O, the distance is called as object distance, U. So this distance between these two points is called as U, symbolize object distance. And the distance between P and I, it is called image distance, the symbol is V. And the distance between P and C, it is called R, radius of curvature. These are the symbols we are using. And these parameters are variables. I told you, if one changes, other also changes. Any change in one of the values changes the values of the other in accordance with this equation. Look at this equation. Is the equation holds good for this refraction at spherical surface. N2, N1, radius of curvature, image distance, object distance. These are the values. This is the equation, left hand side, right hand side. Any change, either it is a variation of R, or variation of U, or variation of N1, or variation of N2. There is also a change in the variation of other value, but in accordance with this equation. This equation always holds good. This is the equation for the refraction at spherical surface. This equation plays an important role in the functioning of lenses in optical instruments. The lenses, the lens, it may be a combination of two spherical surfaces, or it may be a combination of one spherical surface and other is plane surface. The lenses. And these lenses are used in the construction of optical instruments. The optical instruments, as you know, it is a microscope, a telescope, and opticals, eye opticals for eye defect. We are making opticals for eye defect. So all these instruments are the lenses, the functioning. This is the basis. This equation is very important. It is explained. It explains where the image we can get, what size of image we get, and what kind of image we get, that is real image or virtual image. So this expression is the basis for this kind of phenomenon. And this equation is a fundamental for this refraction. We can get this equation by derivation. To derive this equation, we always follow the same diagram is used. The diagram here says there is a point of refraction. For every refraction, what is incident ray, refracted ray. and these are angle of incidence, this is angle of refraction. The law is applicable, law of refraction is applicable. That law is called as Snell's law. What is Snell's law? That is n1 into sine of I equals n2 into sine of r. That is Snell's law. Angle of incidence, refractive index. Angle of refraction, refractive index of the medium. This angle in this medium, this angle in this medium. It is Snell's law. And this is the law and the equation. And this I and this R angle, we can write in terms of the angle, that is alpha, beta, gamma. What are these angles? So these are the angles made with the principal axis. Straight line, that is a ray, incident ray with alpha. That is again straight line normal, making angle beta with the principal axis. This is refracted ray, making angle gamma with the principal axis. We can write them. So it requires that is geometrical knowledge. There is a basic geometry. Look at this. We have the triangles in this diagram. This is a triangle. We have this. And look at this triangle. In this triangle, this angle is an exterior angle because this side is extended, making angle is called exterior angle of this triangle. And these two are its opposite interior angles. These are interior angles opposite to this point. Opposite interior angles. And there is always a formula is there for that. This exterior angle is sum of the opposite interior angle. So I equals alpha plus beta. Recall that equation. That is for any triangle we can write. This is what I have written here. We have written I is equal to alpha and beta. This angle in terms of angle alpha and angle beta. And one more triangle we have. Look at this triangle. This triangle is that. In this triangle, the beta is called as exterior angle because this side is extended, making angle with the other side. It's not exterior angle. If that is the case, these two angles are its opposite interior angles. Then beta equals, same formula I can apply. Beta equals R plus gamma. This is gamma. There is one more equation that means R equals beta minus gamma equation. So it says we can write I and R in terms of alpha and beta and gamma. That is one case. And now we shall go for, can we explain? We can express these angles alpha, beta and gamma as a ratio of the triangle. As a ratio of the triangle by drawing a straight line from this point to this principal axis, that is perpendicular. A perpendicular straight line from this point to the principal axis, like this, by drawing this. Once you draw this line, look at that we have, with this line, we come across three right angle triangles, as alpha is one opposite angle, beta as another opposite angle to the triangle. We have three triangles as opposite angle to the triangle. Look at this alpha, and this triangle is right angle triangle, is opposite angle to this right angle triangle. With this drawing, and with this drawing, same drawing, this becomes another right angle triangle as beta opposite angle. With the same line, we can have one more right angle triangle, gamma as the opposite angle. using tan, because the side, the measurable sides, using tan theta, that is tan alpha, tan beta, tan gamma, we can write as sides of the triangle. What is tan theta? Tan theta, as you know, that opposite by adjacent definition. Opposite side by adjacent side. Now apply tan for all these angles. Tan alpha is equal to opposite divided by adjacent. Opposite divided by adjacent. So opposite angle, there is always one. Let us call this as length m, and length as h, small h. Let us call that value as small h. Here we make small h, that is h written, that is h as the value, and this value is u value. You are making some approximation. Assume that this angle is small, then these two points are getting coincided almost. In that case, this length is a curved length, this length is a straight line, and of course this is a little bit higher than this length. Assume that these two points are coincided. If this line is very close to the principal axis, if that is the case, this length is almost same as this length. Assume that these two points are coincided. Then you can say that this ON almost equal to U. And similarly, we have V and R can be defined. Now, write tan alpha is equal to opposite divided by adjacent. It is U, taken as U. And tan beta for this triangle, opposite divided by adjacent side. This adjacent side is R. H by R. And similarly, we have tan gamma, tan of gamma angle, opposite side divided by adjacent side for this. This is adjacent side, is a distance, is V. That is what you have written here. Tan alpha is equal to H by U, tan beta is equal to H by R, tan gamma is equal to H by V. These angles in terms of I and R, that is angle in terms of the sides of the triangle. Then come to our point. Very important this point. This angle I depends on the inclination of this incident ray. If it is away from the principal axis, angle I is greater. If it is closer to the principal axis, angle I becomes smaller difference. As it approaches, this line approaches closer to the principal axis, we get lower value of I. Correspondingly, we get lower value of R, these two values. These lines approaches closer, this line also approaching closer to the line. If the ray of light is approaching closer to the principal axis, it is also called as optical axis. This ray is called as paraxial ray. What is paraxial ray? Paraxial ray is a light ray traveling closer to the principal axis. Traveling closer to the principal axis like this. They are called paraxial rays. Why you are talking about the paraxial rays? In our practical applications, making lenses, these paraxial rays are predominant. Paraxial rays are predominant. Only these rays are important in functioning of these lenses. So, in this case, if you consider these lines or paraxial lines, the values are very small. Remember the concept. For all paraxial lines, these are predominant in making lenses. These values are very small. Then recall the geometry. What is geometry? If the angle is small, sin theta, in case of sin theta and tan theta, here sin theta equals theta, tan theta equals theta. This is a concept, geometric concept. As the value of theta approaches 0, gets smaller and smaller. As theta approaches 0, sin theta approaches theta. That is, as sin theta equals theta. You can write it as, for a very small value, tan theta equals theta for a very small value. That is geometry. If that is the case, what would be this law? That is, sin I is I only, sin R is R. It reduces to equation N1I equals N2R for all paraxial lines in the spherical refraction. This is what. And one more concept, what is same thing, I said what is tan alpha, tan beta, tan gamma. So tan theta equals theta means tan alpha equals alpha. It is same as the same ratio. Beta, it is same ratio. Tan gamma equals gamma, h by b. And distances are u or v. As you know, recall from the previous classes, these distances are taking sign convention. You always measure from the point P to this point or this point. If the point P from here to here in this direction, from here to here in this direction is in the direction of incident ray. Look at that, in this direction. And these values will take positive values. What about U? It is a measurement from P to V, P to O. It is in the direction opposite to the direction of incident ray. Therefore, this will take negative value. That is why we return U as minus in this case, R as plus or V as plus V. So look at this, finally we have what is alpha, what is beta, what is gamma. Alpha equals this, beta equals this, gamma equals this equation. And we have N1I equals N2R. So already told that is I equals alpha beta. In this case, substitute for I and R. I and R. Here we get this equation. I is this, R equals this. And substitute for alpha and beta as sides like this. That is, substitute for alpha, beta, gamma. This value side. Simplify. H is common factor, left hand side, right hand side getting cancelled. Remaining is this by this equals this by this. And rearrangement, taking left to right, right to left. So rearrangements, I am taking this N2 by V, left becomes plus, and this will remain on the left hand side is minus A overall, this is minus of this one, equals, set this to the right hand side, R value already in the right hand side, that should be there, this is on the right hand side becomes minus. Again further rearrangement, taking R as a common factor, denominator, N2 minus N1 equals R, this is the value, left and right both are same, and this is on the next side, this is the N2 by V, N1 by V. So finally we arrived this equation, same as what this is how we can derive this equation. This equation, the significance as well as derivation. Derivation using the same diagram. Either use a convex surface or concave surface, you arrive at the same equation. So that is the derivation, very important. Derivation of the equation, which finds are crucial crucial for how the lenses function in the optical instruments. With this we have completed. Thank you very much.